All right, guys. My name is Stoliarov. I'm a professor here at the University of Maryland. I welcome everybody here. It's nice and very diverse audience. We're really happy to see you here, and now I can hear myself. You guys, my voice does come out of the speakers, right? Okay, that's a good sign. So before we begin, I want to point out that I think tomorrow we're going to have a lab tour. And if you'd like to participate in one, I would appreciate if you sign up your name and location here. So I'm going to pass that around. Is that, I don't know if Dr. Trouet wants to do any introductions. If not, I'll just move on.
You can jump in.
Okay, great. All right, so I think that Dr. Alex Filkov and Albert Simeoni gave you an excellent overview of wildland fires. And now, at this next slot, we're going to jump in and zoom in some of the physics that are a part of the wildfire process. We're going to talk about things that happens at the surface and inside the fuel elements, solid fuels elements in various fire scenarios. So just to begin, make sure that everybody's on the same page. I'm going to review some of the definitions that I'm going to use in this presentation. First of all, when I refer to chemical reactions that occur inside the solid fuel and ultimately are responsible for the production of gases that feed the flame, I'm going to call it thermal decomposition. Pyrolysis is the word that I'm going to use to describe a coupled process that involves thermal decomposition, but also involves heat and mass transfer inside the fuel packages. And finally, when I talk about ignition, I will primarily focus on the piloted ignitions or flaming ignition of solid surfaces here, just for the purpose of this presentation. So with that out of the way, these are the topics that I'd like to discuss with you today. First of all, I kind of give you a very simple general introduction of the role of pyrolysis and fire growth. We're using very simple bench scale example of this phenomena. Once we clear this out of the way, we're going to talk about simple analytical pyrolysis models that for decades have been a workhorse of our analysis of various fire growth phenomena. Then we're going to talk a little bit in more detail about the processes that contribute to solid fuels pyrolysis and combustion. We're going to connect that to key parameters that define flame ignition, piloted ignition of solid surfaces, and then divert our attention to formulation of comprehensive pyrolysis models that take all of these processes into account. Once we clear this out of the way, we're going to talk some about how we actually obtain parameters for these detailed models. And finally, if we have some extra time, we're going to talk about some of the limitations of these models and sort of things that perhaps we need to focus our attention in the future. We'd like to make improvements in this part of fire dynamics. So here is a little video that kind of designed to demonstrate the role of pyrolysis in flame spread. So on the left, you have a bench scale experiment. You see a plate of solid fuel that ignited by a small gaseous burner that is applied to the bottom of it. On the right, you see a model of this process. And that model shows you temperature distribution inside the solid, sort of at a cross section, and also incident heat flux that's first associated with this gaseous burner, and as this experiment progresses, sort of is replaced by the heat feedback from the very flame that is produced on the surface of this material. So if it lets me play it, and hopefully it does. So what you can see is that that burner starts to heat up the fuel. The temperature of the fuel is increasing gradually, and you see this increase in color associated with this increased temperature. Temperature penetrates and drops. Suddenly the fuel starts to pyrolyze and produce gaseous volatiles. These volatiles evolve, and eventually they produce insufficient quantity to support the flame. As that process now engages in a feedback loop, that more and more heat from that flame goes back into the solid, and as that portion progresses more and more solid, gets involved in the pyrolysis, and the flame grows as a result of it. So basically, one way to look at the fire growth process at that scale is to differentiate between the processes involved in gas phase combustion, the ones that define the flame, and the processes that occurs inside the solid that ultimately responsible for the generation of the fuel that feeds this flame, right? And the connection between these processes are two. You have the heat feedback from the flame to the solid that ultimately causes this thermal decomposition, and you have the mass flux of gaseous volatiles that is the fuel that supports this flame. And that process is going, and depending on the conditions, it can produce in a steady form, it can accelerate or decelerate. And in this particular case, it accelerates because the heat feedback increases as the flame grows and lets, which is ultimately driven by buoyancy. Right? So now we jump and talk about analytical model that focuses on the solid portion of this flame. Now, the easiest way to discuss this analytical model is in a framework of the simple experiment or simple standard test, which is called cone calorimeter. Cone calorimeter is designed to give you sort of a very common scenario that would be an element of many actual complex fire scenarios. In this scenario, you take what is usually 10 by 10 centimeter sample of material, you place it in this holder right here, and you expose it to a well-defined radiative heat flux, anywhere between 20 and 100 kilowatts per meter square that comes from this conical heater. Sort of, if you look at the energy balance at the surface of the solid sample, it's qualitatively represented by the bottom diagram and shows you that you have the heat flux of radiant heat flux from the cone heater, which typically simulates some distant fire. It's usually defined in units of watts or kilowatts per meter square. As this surface of the material starts to heat up, the cool air surrounding this material starts moving because of the buoyancy effect, and it starts cooling the surface away. And as a result of that, you get convective loss associated with this process. And as the surface gets hot enough, the surface starts to radiate. So eventually, those three factors affect what's going into the surface. And ultimately, when the surface reaches sufficient temperature, the ignition forms on the surface of this material. Now, perhaps the easiest way to define this ignition is to make an assumption that that ignition occurs when the surface of the solid material gets to some critical level. Sometimes that temperature is called pyrolysis temperature, sometimes the temperature is called ignition temperature, and here it's expressed as Tp. So if you make this assumption, and I'm not pushing the right button here it is. If you make this assumption that there is such a critical temperature, which is, by the way, material specific, at which when surface temperature is, when material achieves the surface temperature, it ignites, then you can convert this problem of heating basically into a simple heat transfer problem. And there's a couple of additional assumptions, such as, for example, that this material is thermally thick, which effectively means that whatever happens at the back surface of the material doesn't really matter from the point of view of heating. The back surface never really heats up. Then you can show, through fairly simple analysis, that this time to ignition, how long it takes material to ignite, can be represented by this expression here. And basically, you have a few material properties like thermal conductivity, density, and heat capacity that guide these properties. You have this temperature of ignition of pyrolysis, which is called here as Tp. And in this denominator here, you basically have an expression for the net heat flux into the solid before the sample ignite. You have the external radiation from this external heater or from any other external source. You have convective losses, you have convective losses right here, and you have radiative losses from the surface. Now, the challenge here, of course, is that in reality, that what is called their TS, is the temperature of the surface, is a function of time. So it starts out at room temperature and then progressively increases until it reaches to Tp. If you do, however, make an approximation that this losses totally can be approximated by some constant, taking at the temperature somewhere between the initial temperature of the material and Tp, then you can sort of rearrange this equation and dialing back, and also making assumption that emissivity of the surface can be approximated as unity. then you can rearrange this expression into this simple, wonderful arrangement where you can see that 1 over square root of the time to ignition is related to external heat flux in a linear fashion. And that coefficient of relation is this, in this denominator is frequently referred to as thermal response parameter, which combines all the properties related to material thermal conductivity, density, and heat capacity. Well, making this assumption, you produce a tool that can both analyze your data in a device like a cone calorimeter and also a tool that can interpolate or even extrapolate to other flaming conditions other than that are used to study that material of interest. So here is an example of this data. Here you have 2 data sets, both for the same type of wood, Douglas fir, but one is for the sample located along the grain and the other is across the grain. And the difference between that is that wood have different thermal conductivities in those 2 directions. And you can see a set of data points of both of these curves that are generated in a cone calorimeter by just setting multiple tests at different initial heat fluxes and then measuring the time to ignition and approximating it through or fitting it with the expression that is on the left. So the slope of this curve, of course, becomes this expression on the left. So you can, you need probably 3 tests, but you can extract the thermal response parameter, and you can also actually estimate your Q losses if you take this curve and you extrapolate it to 1 over square root to ignition equal to 0. So that creates a model. It's a simple analytical model that can parameterize on a few tests, but it's a model that allows you to determine the time to ignition. Now that experiment, of course, also has a burning phase, and it sort of reflects on a modified diagram that is located on the left. So in the burning phase, you no longer have convective losses because now your sample is covered with the flame. So instead of convective losses, you have additional heat flux that can be convective or radiative depending on the exact size of that flame that adds heat to your system. Now, if you assume, and it's a significant simplifying assumption, that burning rate that occurs after the ignition can be assumed to be approximately steady, then the value of this burning rate, which I have defined as MF, which is typically expressed in kilograms per meter squared per second, so it's a flux of gaseous volatile through the surface, can be determined as the net heat flux through the surface. This is expression in your numerator of this expression, divided by what's commonly referred to as heat of gasification. The heat of gasification is basically the amount of energy that is required to take materials from room temperature through its decomposition. It's composed of 2 terms. First term associated with the sensible heat. This is just simply the energy that is required to heat up the material, and that second part is associated with the heats of reaction that need to take place in order for the material to produce gaseous volatiles. Now, that minus signs may be plus or minus depending on how you define heats of reaction. In this particular case, the negative means endothermic. So endothermic heats are actually added to the overall expression, just for clarity. So if you make this assumption that material burns steadily after it achieved ignition, then you can further analyze this expression, sort of divide it into parts, and note that, again, if we can somehow extract this information from a test, like a cone calorimeter at several external heat fluxes, then the slope of that curve, and this is an example of that analysis, polypropylene, is simply 1 over the heat of gasification. So that allows you to determine that property, and you can also determine this quantity right here from the intercept of this line as well. So just like in the previous case, that model allows you to take several experiments, several simple experiments, and convert it into the model that presumably allows you to both interpolate and extrapolate between various extreme conditions in terms of the burning rate. Now, if you wrap it all up, we're talking about an assumption that the dynamics of a burner of a given solid is expressed like this. Right? You have basically a burning rate that is represented by a square wave, where the start of the square wave is assigned to the time to ignition, and the height of the square wave is determined by your heat of gasification and net heat flux from external sources and the flame on the surface of the material. Now, typically, tests like concalimeter also allows you to obtain heats of combustion of gaseous volatiles. So this information is always available. So if you take this data or this model and multiply it by the heat of combustion, you end up with a heat release rate profile. This which ultimately feeds into a variety of models. So it's a nice, simple framework. It presumably allows to account for the difference in the amount of thickness of material. The integral under this curve really defines what the amount of material per unit surface area that you burn, or to be exact, the amount of material that gasifies per unit surface area. So you can adjust it and you can interpolate it from conditions, but this model also has substantial limitations, of course. And one of the clear limitations, or straightforward, is that for most of the combustible solids, the burning rate or heat release rate or mass loss rate profile doesn't look like a square wave, right? Many times it looks nothing like that. This is especially true for charging materials. So here's an example of the heat release rate measured in a concalimeter for polyvinyl chloride. There's some multiple measurements combined together, and you can see there's sort of that, assuming that the square wave represents that heat release rate requires a lot of imagination. Right? Beyond that, the challenge with this model is that in the process of formulating this analytical expression, we, of course, tend to make very strong approximations of the actual physical reality, starting with the assumption that material ignites at a prescribed temperature. So what this approximation results in is that when you parameterize this model through this analysis, you end up with the values of these properties that do not really match their physical definitions. And because they do not really match their physical definitions, there is a strong possibility that when you extrapolate this model beyond the conditions which examined here, starting, for example, with the conditions where the radiant heat flux changes with time, as an example, you potentially ignite with the results, you end up with the results that really do not correspond to the physical reality. Right. So, what are the actual processes that contribute to the production of the gases of the solids by gases? Let's consider that. Let's sort of take a little bit of a deep in this process. So per our initial definition, we're going to talk about the fact that there is, for the solid to start to thermally degrade, you need some kind of external heat flux. This heat flux can be convective or radiative in nature. And if it's radiative in nature, there is a chance that this heat flux actually penetrates into the depth of the solid. So not all the solids are completely opaque. This is especially true for synthetic polymers, which many of them actually let some radiation in. And if you want to be careful, this is something that needs to be taken into account. Now, as I'm working through this framework, the assumption that I'm going to make is that we're focusing on the processes that occur when the flame covers the solid surface. And that means that these processes are effectively anaerobic because at least continuous laminar diffusion flame consumes all the oxygen before it can reach the surface. Now, that's not true for the part of this process before ignition, and it's also not true for the part of the process after the flaming combustion stops. But this is going to be a focus of a separate presentation here, right? So this processes of direct interaction between oxygen and air and solid is frequently referred to pyrolysis. And Dr. Guillermo Rain, that I don't think is here at this point in time, will tell you everything that you know about it. So my focus here is on aerobic pyrolysis, and it's most relevant to flaming combustion. So if we focus on that, the other thing that happens is a solid, and this is what we observe in the initial slide, is of course there is a considerable heat transport from the part where the energy absorbed into the depth of the solid. Now, this, at least for solid thermoplastic, that heat is primarily transported by conduction. But if you look at the materials that are porous in nature, then the radiation can play significant and sometimes dominant role in this transport as well. Now, in addition to that, we have radiative heat loss that was mentioned on the previous slide. For the materials that are not completely opaque to thermal radiation, that radiation also will also occur from in depth of the solid rather from the surface, and that has impact on the analysis of this process. Now, all that heat incoming to material raises this temperature and triggers a number of the processes that occurs inside. So one obvious set of the processes are phase transitions, talking about glass transitions and melting. The other is, of course, thermal decomposition. Those are the chemical reactions that ultimately are responsible for production of gases, some of which become fuel for your surface flame. Now, all of these processes also set off a change of morphological changes inside the materials, which include charring, which is something that is very familiar with if you ever seen how the wood actually burns, formation of various cracks and fissures and in structures, formations of bubbles, and also potentially a melt flow that associated with the materials that are usually thermoplastics. Those tend to flow. Now, it's important to point out that these processes instead affect the heat transfer inside the solid. So within the solid itself, there is sort of a feedback loop where the heat causes these changes in the solid, and these changes, in fact, affect the heat transfer. And that's what makes the process of analysis of the process both complex and interesting from my point of view. Now, the gases that are produced inside the solid also eventually have to make it back to the surface. And so there is an element in this process that involves gaseous transport. These gases eventually are reaching the surface of the material. And once they reach the surface of the material, they ignite and or burn in the flame that already exists at the surface. So trying to take all these processes into account is the domain of comprehensive pyrolysis models. That's what we do. So we're going to talk about how these models are formulated and how they're parameterized. But before we do, we're going to make a brief stop and talk about how all this physics actually affects the ignitions of the material's surfaces. And here, I'm going to base it on a very simple example. So I'm going to look at the ignition as a condition of existence of a stable flame. And just like about in any kind of sort of traditional combustion framework, I'm going to analyze the stability of that flame based on the energy balance that exists inside. So I'm going to take this control volume that is highlighted by this dashed line right here of the flame sheet, and I'm going to note that when the stable flame exists, the heat production inside this flame sheet divided by the area projected to the surface can be defined by the following expression, where mass fluxes are mass fluxes individual gases, delta H are the heats of combustion of individual gases, and when you sum them up, you end up with total heat release rate in this controlled volume. Now note that I transition from assuming that there is a single gas, a single heat of combustion, to the possibility that there are multiple gases with multiple heats of combustion. So I'm slowly going to the domain of this comprehensive pyrolysis models that fundamentally allow for this to happen. Now, that heat release rate is balanced with heat losses, which is defined by environmental conditions. And in somewhat simplified form here, heat losses are simply the amount of heat that is required to heat the incoming air that enters this control volume from its initial temperature, environmental temperature, to what I call the critical temperature of the flame. Critical temperature of the flame is the minimal temperature of the flame at which flame exists. And that's my attempt not to go into combustion kinetics and start talking about the rates of reaction and things like that. So I've sort of replaced this complexity with a single parameter. Turns out that for many hydrocarbon fuels, for laminar flames, choosing it on the order of 1500 works actually quite well for a wide range of chemistry of the fuels. So you can make this approximation. So this represents the heat losses from this flame. This represents the heat production of the flame. And of course, for the stable flame to exist, in other words, for the ignition to occur, heat release rate should have to be either equal or larger than the heat losses, right? So the point of this analysis is to focus on this. If you trying to understand what kind of physical quantities that are defined through the sources in the condensed phase actually define the ignition, that analysis suggests that there are two. And those are those mass fluxes associated with the mass fluxes of fuel and the heats of combustion of individual fuels. So if you know these two physical quantities, you can actually determine where the ignition occurs. Now, you can do it through simple empirical models that have been developed for specific scenarios. For example, it is very well known by now that if in a scenario similar to a conical emitter where there is no forced flow of any sort, the critical heat release rate of 20-something kilowatts per meter square represent the critical conditions for ignitions. But you can also use these quantities and do much more sophisticated analysis like a full DNS with the kinetics of the flame. Ultimately, in both cases, the input that is required from the point of view of the condensed phase models are those two variables. Right here. So how do we compute those? How do we compute those in complete transient manner, including all these complicated processes that we discussed above? Well, one way to do it is to use comprehensive pyrolysis models. Now, there are a few comprehensive pyrolysis models out there, and I'm going to focus on a model that was developed at UMD because I'm most familiar with it, and this is its basic formulation. So in comprehensive pyrolysis models, you have two equations that solved numerically. They are both transient, and one of them represents conservation of species, and let's say two equations, I mean, the proper way, two sets of equations. So conservation of species, of course, is written for every species that you define in your system, and then the conservation of energy as well. Now, what in this particular case, in the case of thermokin, we formulate these conservation equations using the notion of concentration of species. That's how we track species inside the solid. Now, this concentration of species has the same units as density, but it's not density, right? The density is actually defined in a separate way because within the framework of the model, different types of species can contribute in different ways to the overall volume of the solids. Now, this conservation of species and conservation of energy is defined as a local, with respect to evolution of the local temperature, just like it always is. Now, the phenomena that contribute to both of them are chemical reactions, right? So chemical reactions both affect the conservation of species and also the heats produced or consumed inside the solid. Inside, you also have conduction, you have radiation and re-radiation, and the last two terms in this heat transfer represents the exchange of energy between the solid matrix and the outside source of energy. You have gas transport inside the solid, movement of the gaseous species, although sometimes we can apply this transport equation to non-gaseous species as well, and this transport, of course, can move your component inside the solid, and it can also move heat inside the solid at the same time. And the last term is basically the fact, and that's why this is the key term by which pyrolysis models, I guess, differ from CFD. We most of the time we're dealing with the system which either shrinks or expands as a function of times as undergoes pyrolysis process. So there is a movement of the mesh that takes place. And these equations are traditionally formulated in Eulerian framework, which means that that movement causes actually movement of mass and heat against this framework, and that's what this last term basically takes into account. Now, if you look at a few more details, reaction rates. Reaction rates inside the solids are typically expressed using the Arrhenius form. So this is your A pre-exponential factor in E, the activation energy. In Thermokin, these reaction expressions are related to the same quantity that is used for the conservation of species, that concentrations expressed in kilograms per meter cube. In Thermokin, the reactions can be of first or second order, which means that you either have one reacting species or two. And if there are two, you can have different species reacted to each other, or you can have the same species reacted to each other. And depending on how those reactions are set, you have either first or second dependence on the concentration. And by the way, that reaction between two different species become handy when you analyze certain type of systems, and we'll circle back to it in a little bit when we talk about the parameterization of this model. The gas transport is typically expressed here by the driving force of the gas transport is the concentration of species expressed as a volumetric fraction. Effectively, this expression gives you, depending on, let me circle back, depending on how you define the volume of your solid with respect to the concentration of individual species, this transport mechanism either approximated Darcy's law, which is pressure-driven viscous transport through the porous matrix, or it's defined sort of represents standard classical diffusion. And last but not the least, the radiative transport terms. We have this generalized form of Beer-Lambert law right here. The only perhaps difference from the traditional formulations of some of these expressions is that we use the mass-based concentrations as describing the quantities of species. That's why our absorption coefficients are actually normalized by density. And we have finally this radiation expression, and not going to detail of formulation, I want to point out that the reason it's formulated this way is to ensure that the very same solid elements that absorb radiation from outside also emit radiations in the same proportion. And that ensures that your problem is compliant with the second law of thermodynamics. In other words, you do not create any possibility that the temperature of the body that is being heated rises above the temperature of the body that is the heat source. Now, you probably have noticed that these equations have a lot of parameters in them. And those parameters, some of them are apparent, like initial material density, and some of them are not clear how to measure and to determine. So a lot of work in the field of fire in the past 15 to 20 years have been focused on figuring out how to parameterize these detailed pyrolysis models that in principle give you access to all this complex phenomena that you can balance against each other. And one of these approaches have been developed by Chris Lautenberger, who is right here in front row, right? And his co-authors. And the idea of this approach is that you start by assuming the thermal decomposition mechanism of desired level of complexity for this material, and subsequently you do something that is somewhat similar to the way you parameterize model for the analytical formulations. In other words, you take a set of fire calorimetry experiments, such as cone calorimeter, but unlike in the previous case, we only had a couple of parameters that you can easily fit into this general data. Here you fit the whole curves as generated with these parameters that you define in this model. So here is an example of this results from the reference paper. It shows you how pyrolysis model of red oak is parameterized based on the calorimetry data. Here the parameters of these models are fitted into actual mass loss rate profiles and also into simultaneous surface temperature measurements that is shown on the right for two different heat fluxes. Okay. So there are, well, one obvious advantage of this approach with respect to analytical models, as you can see, that we now can actually capture the shapes of the curve that corresponds to the mass loss rate. So we no longer have to assume that square wave type assumption about the burning rate. But disadvantages doesn't come without a cost. One of them is that the problem of finding the sets of parameters that define this model becomes more difficult, right? You can assume various levels of complexity with which you start with, but even if you assume a single thermal decomposition reaction here, you have something on order of 10 parameters that you need to obtain in order for you to generate these predictions, right? So that means that you have to search 10-dimensional space for a possible combination of parameters that gives you acceptable result. Now, using simple optimization algorithms such as steepened descent do not really work in these highly multidimensional problems. So the authors of this publication spent some time identifying a technique that gives you more effective access to optimization. And I think what was identified is a group of the algorithms that generally refer to genetic algorithms. And it was shown both through Chris's work and a number of subsequent studies that for these types of problems, this algorithm worked quite well. So the idea of these algorithms, and you can ask Chris about details about it, but I give you just in general terms, it combines sort of Monte Carlo type approach where you generate sets of parameters randomly, right? Then with a selection where the parameter sets that perform best serve as a foundation for the parameter sets that become next. So you kind of make these parameters together, and this way you simulate the process of natural selection to give you the best results. So that as a result of that, you can optimize these complex data sets, and as you can see, produce rather high quality fits. Now, the other challenge with this approach is the same as was associated with the original model, is that because you have limited amount of data and you have so many parameters, it's always hard to say with certainty to what degree the optimized parameters define this data. In other words, to what degree these parameters that derive this way actually represent the physical phenomena that occur in this system. And I think that to a large degree depends on the quality and availability of the data. The more data you have for this type of optimization, the more types you have this optimization, the more conditions you explore during this analysis of the data, the more likely your parameter sets become carry as much a lot of physical meaning associated with them. But if the data is limited, then your parameter sets is limited, potentially, with the ability to extrapolate. All right. So another way in which you can parameterize these models is called hierarchical approach. And this is something that we have been working here for the University of Maryland for a number of years. And the idea is the reason it's called hierarchical approach is because it's based on a set of tests or experiments where the results of analysis of the previous test serve as the input for the analysis of the next test. So you kind of construct your model in layers until you have a fully parameterized model that you subsequently validate. I'll demonstrate this process on a particular example. So typically in a hierarchical approach, we start with the test that focuses on a problem without any transport, right? So we're trying to find an experiment where we can look at the thermal decomposition process without the effects of either mass or heat transport. And one standard technique that gives us this access is thermogravimetric analysis. Now, for those of you who are not familiar with this technique, this is where you take a milligram-sized sample and you heat it linearly with time in a very well-defined atmosphere. Most of the time we use nitrogen because we're approximating this burning of the solids underneath the flame. And as you heat this sample up, you measure its mass as a function of time. So the results of these measurements, for example, for a simple material system of polybutadiene terephthalate and glass fiber are shown on the right. So you have your mass loss rate and also mass as well at the same time. And then when you obtain this data and you certain that mass or any transport processes were not a factor, that this is a signature of thermal decomposition, you try to come up with a mechanism that approximates this thermal decomposition to your best ability. And basically, in this particular case, there is a single well-defined peak. So we know from our experiment that this experience that our decomposition can be captured by a single reaction like this. Polybutadiene terephthalate forms residue and gaseous species. You can guess your initial Arrhenius parameters from just by looking at the height and the position of temperature, and then you can do a slight optimization of these parameters, which is very straightforward. You can done manually. Just about any optimization algorithm can handle it really well. When you do that, you get the resulting fit, which allows you to determine both of the kinetic parameters associated with that system, right? So that allows you simple parameterization of the kinetic portion of this model without looking at any other aspect of the problem. I must point out that that problem is not always the traces do not always look this simple. Here is an example of polyvinyl chloride, which looks more complex, and here we use 6 consecutive reactions to fully capture that trend, right? So sometimes we do that, and more recently, we start looking at using this type of approach to look at actual interactions between the gas phase species inside the solid. So I'm not going to go in details, but I'll give you just a flavor of it. This is an example of a system containing of nylon 6,6 and red phosphorus. And the main feature of the system that phosphorus actually acts flame retardant because it actually reacts with nylon. And it increases production of char and so on and so forth. So we demonstrated that by looking at the thermal decomposition of nylon 6,6 in a pure form and red phosphorus in a TGA that actually sublimes in this particular case, and then combining these two kinetics and looking at the kinetics of the blends and comparing what we predict based on the assumption that those are non-reactive mixtures and what the experimental results actually show, we can actually identify chemical interaction between the species and incorporate this in mechanism. So this mechanism, what the end result of this whole exercise is the 9-reaction mechanism that actually allows you to predict how this material both decomposes and pyrolyzes as a function of the composition. So I can basically change the amount of red phosphorus in my model, and I can predict what the TGA trace it will look like. Actually, I can predict the burning rate as well, which requires a few more layers that we're about to walk through. So once we're done with the development of the mechanism based on the mass loss rate, then we focus on the heat flow data that are typically extracted with an instrument which is called differential scanning calorimeter. So differential scanning calorimeter, or DSC, can be a standalone test, or it can be conducted simultaneously with the TGA, as it was done in this particular case. It's a much more trickier experiment than a TGA because it requires careful calibration and analysis of baselines and conditions and so on and so forth. But provided that it's done right, you can actually extract information about the heat flow into the sample, like is shown here. That includes information about both the sensible and latent heat, right? So what is shown on the right is the amount of heat that is required first to heat up the sample at a constant heating rate, then melt the sample, and then subsequently decompose the sample. So in the expression, what you see is the expression on the left shows you the contributors to this heat flow curves. So if you take the model, thermal decomposition model that we developed based on TGA, and this is sort of where hierarchical comes into play, because we use the data from the previous analysis to analyze this data. So we use the thermal decomposition data to simulate this baseline curve. We can adjust the heat capacities of our reactants and products to match the results, and that now we have the information about these heat capacities. Now we can integrate the corresponding peaks, and we can have reactions on the heats of reaction and corresponding heats of melting. We tie it all together. We are very careful here. We want to make sure that we don't make any assumption about this test. We take the fact that in this test, the heating rate is not perfectly set into account, which allows us to extract heat capacities of the sample near the room temperature. When we get it all together, we have a model that successfully predicts that heat flow throughout. Okay? So this is associated with parameterization of thermodynamic reactions that occur inside the solid. Once we've done with that, we perform much more set of testing that looks at the heats of combustion of gases that we defined in this model, right? So this is our new mechanism. It includes the melting step that describes that melting peak, and then we move on. And our next test is called microscale combustion calorimeter. This is also a milligram size test. It's very similar in TGA in the idea, but unlike the TGA, you're measuring the heat produced as a result of combustion of gaseous volatiles, and you also plot it as a function of temperature of the sample. Now, that instrument can be analyzed using the model that we built on the basis of TGA and DSC. So here is an example of this analysis that is done for polyisocyanated foam. And the reason I switched the materials here is because polyisocyanated foam has much more exciting TGA trace than polybutyl terephthalate that has a single peak. So that material has a complex behavior. As you can see, when we model as TGA, we identify 7 different reactions that contributes to that profile. And then we simulate MCC heat flow in these materials. And what we basically do is we match the heats of combustion of individual gases that we define in the model to make sure that we reproduce MCC trace. And as you can see from the fact that those traces are not exactly equal to each other in the profile and shape, that those heat of combustions actually differ. So assumptions of the same heat of combustion for all gases that involve at all temperatures would not produce a good fit here. So this is the only test that I know of where that allows you to differentiate between the heats of combustion of different components that evolve from solid materials at different points of time, or different points in temperature. So once we are armed with this information, then we proceed next step, and now we'll look at the transport of heat and mass inside the solid. So by now we have parameterized all the kinetics and thermodynamics of the thermal decomposition. We determine the heats of combustion. So our next stop is this test right here. So what we try to do here is to design our own apparatus that looks at the thermally thick burning problem, but tries to define or tries to create a test where experiments of all boundary conditions are defined really well throughout the test. And we can measure few things at the same time in a relatively easy fashion. So what we have here is a 7 centimeter type disk, and you will see this instrument during the lab tour that put in this thermostated chamber. Those experiments are usually run on nitrogen. You subject it to a well-defined radiant heat flux, and you simultaneously measure back surface temperature of this material. You measure its thickness as a function of time, and you measure mass loss from these materials. So the key feature of this experiment is that all the boundary conditions at the top and the bottom are very well defined, and you know them. We do have a few additional tests that we do. For example, we characterize the total broadband emissivity of the surface before we get here, and we also quantify the absorptive characteristics of these materials. But with this defined, we now have an experiment where all the boundary conditions up top and bottom defined. We know the shape of the sample that evolves with time. We can actually track changes in the boundary conditions as the shape of the sample changed, as it shown here on the example on the bottom. And the only unknown quantities now in this test is that conduction term right here, that associated with heat transport to the sample, right? What we have, of course, is the back surface temperature of the materials with all defined boundary conditions. So we don't have conductivities, we have everything else, we have heats of reaction, we have reaction rates, and all of that is already parameterized. So it allows us to, in a fairly straightforward fashion, to determine the thermal conductivities that give us correct prediction of this temperature profile. So that's done through sort of a set of straightforward iterations. Those iterations can be done manually. They can be automated. We have both tools available to us. But ultimately, at the end, you adjust thermal conductivity until you get a good match. Right? Once you've done that, you actually have the pyrolysis model that is fully formulated. You have all the dissociation elements of the surface. You have kinetics. You have thermodynamics. You have transport processes. And as a last step, you attempt to predict whether or not the mass loss rates that measured in this non-thermally thin experience are actually correctly represented by the model. So here is an example where they do, right? So if you complete this parameterization and you find the result like this, where the model predicts the mass loss rate in this non-thermally thin gasification experience, effectively you married your kinetics that you measured in milligram scale tests with your transport properties that you measured at this scale, and thought that when they work together, they actually give you the right results. You can feel fairly confident that the model should work. Now, I always get this question as to, does it always work like that? And the answer is no, it doesn't, right? But I do want to point out that when it doesn't work like that, very frequently it tells us something important about the system that we eventually would like to learn. Right? And here is one example of that. Right? So what I showed you is just a moment ago is a trace for pure polybutyl terephthalate. Here's a trace for glass-filled polybutyl terephthalate. And the reason, the difference is really is that chopped glass that is located in this sample. And we actually changed the thermal conductivity of this chopped glass to perfectly capture that temperature. Right? So and we think, well, with that, we should be able to capture mass loss rate from this material because we already know everything about it. But turns out we don't. We actually underestimate that mass loss rate quite a bit by the model. This is your green curve. And the question is why? Right? So that type of result seemed to be discouraging at first, but it actually helps us understand how this material behaves, because what we did in this particular case is went to the literature and noted that many people noted that when you fill those type of materials, the materials that melt with glass, the heat release rate actually jumps up instead of what you would expect it is to coming down, because seemingly you dilute this material with an inert substance, right? You should have less heat release rate, and it goes up. And the speculation that was put forward is that the glass actually acts as a wick. In other words, the glass residue, the sort of the scaffold that left behind as the molten polymer actually helps wick the polymer towards the surface. So you have a little pump inside the material that brings this molten polymer to the surface. It vaporizes, and the result of that, you have that peak, right? So we actually studied that, right? We dissected our sample after pyrolysis and learned that the amount of char that formed at the top portion of this glass sample is actually considerably larger than what it should have been if the polymer was distributed evenly throughout, right? So then we added that effect of mass transfer of the molten PBT through the sample, and we were able to capture it quite well. Okay. So with that, let me now, so this represents example of the hierarchical approach to the pyrolysis models and gives you an understanding how this model parameterized. And the question now that I'd like to talk about is, like we have all these methods, do we actually do things well at this point in time? Can we actually assume that that on average, as a community, we can parameterize those various motility with a reasonable degree of precision? So we looked at this question at a very recent study. Well, what we tried to do basically is to see, we looked at all the information available on a variety of combustible solids and tried to understand how uncertain they are from the point of view of people who measure those properties, and whether these uncertainties that they estimate actually translate to reasonable fire growth predictions, or whether these uncertainties indicate that our fire growth predictions would indicate that our measurements are not sufficiently robust to make these fire predictions with certainty. So to do this, we focused on this type of systems. So as our target simulation, we choose an approximation of a room corner test. So for those of you who are not familiar with it, it's a test for the wall lining materials that is where 40 kilowatt burner is placed next to the vertical wall corner, and the burner is ignited for a certain period of time, and then you determine whether that material spreads the flame and what rate it spreads on. Now, typically it's called is done in an enclosed room, but in this particular case, we sort of looked at the open corner scenario, just so that our problem was dominated by the material itself and not the formation of the smoke layer and all of this other things that we've done here. So when we looked at this problem, the first thing was what is our reference point? So we're going to look at the uncertainties of various properties and the impact on the results of the spread. But how do we define this material from which we start with? And to do that, we kind of took 26 different materials for which we found reasonably complete set of properties, and we kind of generated the average material out of that. So take these properties for each class of properties, such as heat capacity or heat capacity of char. We average those out, and we determine what this average, albeit not existing materials, looks like and what their properties are. And then we'll look at what different people report as uncertainties in these properties and try to come up with the average value of uncertainties that represents that. One interesting thing that occurred during this analysis I want to point out here is that if you try to estimate the uncertainties of kinetic parameters like E and E, and we're talking about here a framework, we assume that everything decomposes through one reaction, which is sort of simplistic, but that's the way we have to resort to in order to make sense out of these results. So if you look, at sets of data, so what we've done is we looked at sets of A's and E's for presumably the same material. So here is an example: is polylactic acid. There is several studies out there that measures those A and E's, and if you look at this old data, you see a lot of scatter between these data. In fact, you see about 12 orders of magnitude in A and about 70 kilojoules per mole in E, which is, if you take that, it's tremendous. It's really the kinetics that basically includes just about any materials you can find, more or less. But the interesting feature of that is that, those properties are actually correlated, right? They're not really, they're not really occupying that square. They only occupy this narrow strip right here. And that's associated with so-called compensation effect. Now, compensation effect is something that people in the literature have been argued for decades as to where it comes from exactly. But, and I'm not going to add to that calamity. I'm just want to point out that it's there, okay? So the implication here is that when you're looking at the impact of A and E uncertainties on the results, you really want to make sure that you move your things along that rectangle and not outside of it, because the rest doesn't really represent reality. So in result of that, this A and E becomes a coupled parameters, right? It's not completely independent one from the other, and you have to have this coupling into account, and this is how sort of it's analyzed here, shown on the right-hand side. So when you take uncertainties in various parameters that we measured, uncertainties reported according to people that measure it. So that's probably better estimation of uncertainties than they really are. And you try to understand how impactful these uncertainties are on the rate of spread in this test on the left, which is sort of our key category when we're looking at the rate of the fire growth, average rate of spread. The diagram probably on the top is a thermokin, on the FDS. My point here, they all give you more or less the same results. Both of them indicate that the property that we don't measure well are kinetics. Okay, this A's and E's we don't measure well. Even with the existing TGA tools, we don't really measure sufficiently well based on the scatter available in the literature. And these properties can have substantial impact on this prediction. So this is where we can do better. Okay, the second thing that where we can do better, somewhat surprisingly to me, is the heat capacity of the virgin material. We seem to, there is a fairly large set of standard material science tools that measure this property. Yet those uncertainties that come out of this tool on order of 10-15% are large enough to put us significantly off track when you're trying to do this measurement. So this is another material properties which we really need to understand better. Okay. Now, I'm still have time, right?
Yeah, you're still speaking.
All right. That's not correlated to each other. Still.
You have half hour, but
right.
you should include questions.
Okay, I'm gonna wrap up soon. Okay, so what I want to bring up is that so we talked. So when you're looking at how well we're doing this pyrolysis modeling, the one aspect that we just discussed is that among the properties that we measure, some of these properties, namely kinetics of thermal decomposition reactions and heat capacity of the virgin materials, is something that we need improvement on. The other thing that I think stands between us and ability of the measuring these properties at with accuracy is some of the phenomena that do not necessarily clearly manifest itself at the scales at which we parameterize our models. Now, that's a very broad statement, and there are very many examples of that in the literature where people do bench scale measurements of various properties of the combustible material and then try to produce a full-scale simulation of the fire growth on the wall, something like that, and find out that there are things that really do not show up at all in this test that suddenly become prominent features of that large-scale experiments. Now here, I'm going to give you a simple example that we actually experienced in this lab that demonstrates that to a degree. So so one of the materials, and I think that I already mentioned briefly, that we studied here was polyisocyanurate foam. It's an insulation material that goes inside of those cladding panels that are put on the buildings and sometimes spread fires really well on the building. Now, I do want to point out that PIR foam by itself is not a particularly flammable material. It's actually pretty flame resistant, but in these systems it's also combined with polyethylene, which makes it an interesting flame and highly flammable combination. But here we focus on PIR foam, and we parameterize it based on the principle that I just outlined. So we went and measured kinetics, we measured thermodynamics, we looked at the kappa data and made sure that our mass loss rates from this PIR tests and predicted well, and so on and so forth. And then we tried to actually make predictions of the behavior of this material, of its spread on a vertical wall, which was about 2 meters tall, and it was pure PIR panel. So when we started doing that, we were significantly off. And we were trying to understand where exactly we made a mistake in this particular case. And what turned out to be the case that we kind of, the way the source of this discrepancy is revealed is when we took, instead of taking 1.3 thick centimeter sample and put it in our kappa test, we took 2.5 centimeter thick samples and put it in a concalameter, okay? The difference is thickness, right? So when we did that, we found that even at that scale, those thicker sample heat release rate was considerably larger than what we predicted by the model. So we tried to understand why is the case, and it turns out that that has to do with the blowing agent that they use in the foam. So, and that's counterintuitive because blowing agent is a gas, right? So it's 1,000 times less dense than the solid. How much blowing agent can you actually have in a foam like that? Well, there are two issues here. First of all, this blowing agent is isopentane, which is highly flammable gas, not just a gas. And the gases that are actually, well, the PRI gases have a heat of combustion on the order of 10 to 12 kilojoules per gram, and isopentane is almost 50. Right? So it's 5 times higher in the heat of combustion, and the foam itself is actually not 1,000 times less dense, but it's only 100 times less dense. So once you look at the low density, low flammability matrix, and you just add a little bit of gaseous agent, it actually has a pretty profound impact on your heat release rate, right? And it's right here, right? So this, when you include the appropriate amount of this gaseous added in the model, you actually hit the integral heat release rate, and without it, it don't. And in the sample that we examined in the camera, we didn't really have any gaseous agent left. because when you cut it to that thickness, most of it actually goes away. So this is something where you wouldn't think off the top of your head that you would lose that feature of the material when you're doing that, but in fact you do. And it has an impact that makes a difference, right? So if you look at the flame spread rate and you use that model that we originally parameterized, your peak is an order of 50, the real peak is an order of 70, so you mismatch it by almost a factor of 2. But once you add that blowing agent, you end up with something that is considerably closer to the actual heat release rate. Right. So that demonstrates, again, this is one of the multiple examples that demonstrates you that with all these techniques that we're doing in the bench scale, we're frequently missing some aspects of the behavior of material that manifested themselves at a full scale. And how to appropriately take it into account is something that we still need to understand. I mean, ultimately, we would not want to do full-scale tests as a part of this process, right? Those are expensive, those are difficult to do, so we have to find another way. We have to find a way where we have the understanding of what happens in the full scale, gain the understanding of the full scale based on experiments, and appropriately incorporate it in our pyrolysis models. Right? So with that, here are some simple, clear conclusions, and I'm going to leave time for questions. First of all, I do want to point out that comprehensive pyrolysis models that have been developed during the past few decades do provide much greater ability for us to model the fuels. And I think they represent the path to the future for all kinds of engineering and scientific problems. I think that one of the current things that we can address and should work on is to figure out how to measure the properties that go into these models better. So I think basically our focus should not necessarily be on the development of the models, but rather on the development of high quality, reproducible, and interpretable measurements that will form the foundation of these model parameterization techniques. I think we need to figure out how to homogenize the approaches to this property development across the community. We all do it right now in different ways and come up with a set of best practices. I think that alone will take us, will be a substantial step forward. And finally, the last but not the least, I think our next modeling challenge is to take what we have with these comprehensive pyrolysis models and combine it with the mechanical models of the mechanical behavior that account for both deformation, bulking, and melt flow of these materials. In certain scenarios, those types of behaviors from the solids dominate overall progression of fire. And if we'd like to be able to model the fire from the beginning to the very end, being able to model these processes together becomes critical. I think we have a fairly sophisticated mechanical models in the standalone mode. We have fairly sophisticated pyrolysis models in the standalone mode. I don't think we have any models that do both well and in detail. And I think that represents sort of the next frontier from the point of modeling. With that, I would like to thank you for your attention, and I will be happy to answer any questions that you might have.
Session is open for questions.
Okay, thank you for the presentation. In the case of glass week, that you were telling about the discrepancy between the model and the actual results, how come there is such a big difference in the size of area under the curve for the, because this is mass loss rate, so it's a
Yes.
finite amount of mass, and it should, I would imagine, it would be the same area under the curve. Where is this?
Okay, good question. So the question is, why is there difference in area between the modeled mass loss rate curve in this particular case, which is the green line, and the experimental result, which is the dots in this particular case? And the answer to that is because the sample thickness in this particular case doesn't change with time. Basically, whenever material recedes, the glass fiber actually remains in a fixed scaffold. It kind of acts as a char, although it's not a char in a conventional way, right? So if you just take into account that, then the material that recedes far enough that at some point the temperature on the back does not get hot enough for this material to fully decompose. So you basically, in the model, you end up with undecomposed material, whereas in reality, all material fully decomposes.
Thank you.
Yes?
You mentioned that, not a problem with the model, but you said that either the capacitance or the conductivity is a big source of error, and because we don't have a good way of modeling it, of measuring it. Is that a limitation in our current experimental capabilities, or is it a limitation of assuming that it is constant through a range of temperatures?
So, good question as well. So the question is that in the study of sensitivity to uncertainties that we talked about right here, that study suggests that among the uncertainties of various parameters, one of the parameters that impacts most our prediction is heat capacity of the virgin solid. And the question is it because we don't measure it well, or because we make an assumption about its that this heat capacity is a constant, non-temperature dependent quantity? And the answer to that is that in this particular model, we in fact take into account dependence of heat capacity on temperature. So you see the red line here? It actually what we feed into the model. So this data are the heat capacity dependence on temperature for a variety of materials. They all were taken as a temperature dependent, and our average model takes into account that as a temperature dependent. So there is no limitation without this model that the heat capacity doesn't depend on temperature. We assume within the model that it's linearly dependent on temperature. But the main reason why we're so sensitive to heat capacity is because it is a difficult measurement to do well. It's experimentally difficult to obtain measurement of the heat capacity within the uncertainty of about 10% or less. It's even more difficult to get this data well at elevated temperatures. Okay, so you do need this temperature data over a range of temperatures, as much of a range as you can have. These measurements are impacted by the fact that at elevated temperatures, the material may actually go through some shape changes and some changes that actually may interfere with, for example, your thermal content that we use in this measurement and so on and so forth. So we do not measure this. We do not measure this temperature. We do not measure this property sufficiently well, and partially we don't do it because it is a temperature-dependent property. Yes.
Yeah, thank you for the presentation. It's an interesting framework for continuous pyrolyzing fuel. But do you have any suggestions or envision any challenges in creating a similar framework for a discontinuous charring fuel, like vegetation, for example?
I think Dr. Truvek has created that framework, okay. Right? But what I want to point out, so the question is whether this framework work well for discontinuous. You're talking about particulate type fuels, right? So I think that from the point of view of the processes that we derive that is free of the transport, right? So we're talking about the kinetics and thermodynamics of thermal decomposition and all of that. I think this method works just as well. Now, in the process of doing that, when you analyze these properties with these experiments, you have to create a sample with a good thermal contact, which means you cannot put leaves in your TGA, right? You have to destroy the sample to some degree. Now, you can do interesting things with that, and people have done that already. Like you can try to cut out little representative chunks of actual materials and try to see how that impacts the results and all of that. But ultimately, in the TGA and DEC type of experiments, you want material that has uniform temperature that you can control. And that puts certain limitations on what you can do with the samples. Now, trying to understand the impact of the transport in this particular case is a more complicated matter. Now, we can certainly apply this methodology to solid wood and wood-based products. In fact, we've done it, right, for a number of wood types materials. So that's straightforward. But if you ask me how to parameterize non-thermally thin behaviors of branches, right, and leaves and needles and all of that, here I don't have a good answer for you. I have to think about that, right? So I think that in principle, the methodology, the framework of modeling is the same. But how do you account for the non-thermally thin behavior of these fuels of complicated shapes? How do you measure it? How do you quantify it? That's a question that is not straightforward to answer, because you always want to do these experiments in such a way that where the boundary conditions are perfectly controlled. Only then you get insight in what's going on really inside, right? But when it's perfectly controlled, it means that you want to like nice flat surfaces and solid things, and that's how you can actually do it effectively. If you have some solid sample that is sort of a branch that looks like this, and then there are challenges associated with that. I'm not saying it's impossible, but I think that part of the problem, at least I would have to think of how to address.
So kind of like change the fuel into something that works in this and then get the material.
Kinetics, you can kind of mush it and create kinetic, right? And then again, there's this question of whether when you're mushing it, do you actually destroy something chemically? But if we take it aside, then you can probably do that. And then you want to try to create the conditions where transport inside these fuels plays a role, right? But at the same time, you measure something meaningful and you control these conditions very well. And off the top of my head, I'm thinking about maybe some convective exposure, which very well defined airflow with very well defined temperature of the flow, where you can then, knowing the geometry of things, you can actually infer what's going on inside. Sarah, you did something similar to that, right?
Yeah. Well, I think live fuels presents its own problem, because much like your structure with your glass fibers, there's so a lot of structure in just even a single needle or leaf that once you look at like milligram scale, you have to destroy. But that might be really important to how it burns at full scale.
Right.
So,
And
challenges.
Right.
But part of this, I'm going to add something to the discussion, because part of this, so if I consider that the fuel elements are cylinders in shape, to simplify, so when they are very large, you're taking a log of wood, then the methods, of looking at 10 by 10 centimeters square sample of the material, heating it with a radiant panel, deploying the instrumentation and methodologies described by Dr. Stoliarov, I think they apply. It doesn't matter whether you're doing structure fires or wildland fires. But the problem is that looking now at a 1 millimeter size or even below a piece of vegetation, then you have effects that have been characterized actually by Dr. McPhinney and Sarah McAllister here, where they show that the relative weight of radiation and convection changes. And so now you have to be careful about this factor H that appears in some of the equation. It's not going to be the same and strongly dependent on size. So there you have, for example, if you look at the critical heat flux to ignite a table of wood, it's on the order of 10 kilowatt per meter square, roughly speaking. Now, if you take the same table and reduce it to a small sample that is 1 millimeter cylinder, then it's going to be 30 kilowatt per meter square. So it's not the same. Okay, it's not the same problem. And that's due to the change in convectivity transfer. I think something that probably, Sarah, I'm not trying to give you the hot baby or your hot potato, but you're going to talk about it, I think, tomorrow morning.
Yes.
Any other questions? Yes.
Hi, Professor. I'm curious, how do you include a weight effect in your models to increase the mass loss? So by changing the properties of materials or add some factors.
So the question is, how do I include width effect in my model? Can you be a little bit more specific and point to particular example? You're talking about, for example, these simulations here?
Yes, because the green line is without a weak effect, right?
Or you're talking about wick effect?
Yes, I wonder how do you include this weak effect?
Okay, got you. Oh, yeah, I understand. So the way I include wick effect in this model was assign a transport to my melt. So in the model, I defined melt as a part of my equation. So actually, one of the components was molten PBT. And in my initial model, I assumed that the model PBT was immobile. In other words, it just stayed where it was formed, initially decomposed. But in my second iteration right here, what I did, I assumed that my PBT actually, molten PBT, can actually transport from the low, and basically transport was diffusive in nature. So it's tried to be driven in such a way that its concentration was uniform inside the matrix of the glass. And the rate of this transport I parameterized based on my observation. So once material makes this wick, and once material makes the melt, and once you evaporated some of the smell from the surface, that melt starts moving from the bottom of the material toward the top of the material.
Thank you.
Yes.
Thank you for the presentation. I want to ask if the model you have discussed so far is applicable to materials that do not ignite during combustion. So I'm literally talking about smoldering combustion. So can we apply this model for those materials?
Okay, so that's the question is whether the model like this can be applied to smoldering combustion. And the answer in general is yes. It has all the components that you need to be able to simulate smoldering combustion. However, parameterization of the smoldering combustion is a different problem, right? So here, in this model, I don't have any parameters that define the parameters that you need to be able to define smoldering combustion. Smoldering combustion is a process where your oxidizer, your oxygen, interacts directly with your matrix of your solid, right? So in my model, there is no reactions, at least in a way that actually define this interaction. If I add those reactions, that has to be based on some kind of experimental observations, then I can do it. For example, I think Chris, in one of his subsequent works, did that fact, right? You guys looked at concalorimetry-like experiment where instead of sample being exposed to, effectively you had sample that was exposed both inert and oxidative atmospheres. And they looked at the temperature, and like these experiments were done at NIST. They looked at temperature inside the solid and mass loss rate, right? So you had a series of experiments which involved different types of conditions in terms of oxidizer present in direct contact with the solid, and you have mass loss rate and temperature data for all these things. Now this data contain information about that oxidative pyrolysis, and now you can make an assumption about what these oxidative reactions are. In the simplest case, you can say my char that forms the result of pyrolysis will react with oxygen to form gaseous products, right? It's a simple assumption that you can make, and then you can parameterize this additional reactions based on what you observe in these oxidative experiments. So this is one way in which you can extrapolate. Now, I do want to point out that we are still really learning how to parameterize pyrolysis models that do both things well, okay? We are nowhere near the point where we have a well worked out workflow for the model that does both burning and oxidative pyrolysis or smoldering well and things in between. For example, we would really like to have models that can simulate transition between burning and smoldering and back, right? We're not really there yet at that point in time. But this is one of the key challenges that we would like to address in the near future. And I think that especially if we'd like to model the wildland fire, because that's where the problem becomes very central.
Yeah, I would just like to add a comment to what you were saying and the question that was asked to you before. I mean, there is a whole body of literature in which people put wildland fuel in GGA, DSC. Usually they're dry, you know, they're dead vegetation, and they're just grind it, you know, to do it as a powder. And of course, it's creating problems and how it's going to represent the actual, you know, ignition process for a fuel which is made of cells and of a live material. But there was some degree of success to implement models with these parameters, and you can find, I think, there are even several review papers on that that have been published. And then when you're getting to the next scale, you know, because of this problem of the porosity that you are mentioning and the different thermal thickness and even, I would say, the adequacy of the usual correlations that we use for convective and radiative heating for such thin particles, people try to design experiments where they can prescribe a little bit the geometry, you know. So for instance, there were experiments that were done in France where they were looking by the team of Pascal Boulet, where they were looking at the radiative properties of the needles, and they aligned them perfectly, you know. We've done experiments in the FPA where we block the convection and things like that. And then even Dr. Filkov used the inverse modeling, you know, to get some of the properties. So you will have, with the wildland fuel, to get some degree of manipulation to simplify your problem and to be able to characterize some of the aspects.
Right, right. No, that's absolutely true. I think that challenges of the geometry of these fuels remains. I still think that designing the models that can simultaneously reproduce smoldering and flaming combustion is an easier task than going toward you know, complex shapes of real vegetation. I think that is probably a lower hanging fruit. Like at least we will learn how to do logs right and things like that. You know? And I think I would just focus on that because I at least see clearly past that as attainable. I think the big challenge, as you point out in these things, that when you look at this complex shape, right, defining the boundary conditions becomes very, very difficult task. Designing experiments with a clear defined boundary conditions becomes very, you know, questions about the validity of these correlations and things like that, they would haunt us for a while in this kind of environment. So I think that logs first, you know, twigs later, even though I know that twigs are important.
One last question? Well, if not, let's thank Dr. Stoliarov again.